I am Anil Kumar. Welcome to my series on kinematics. We'll discuss position time graph in this particular video. If you want to learn from me, you can always send an email on the address given. Our website is being uploaded with new videos, so you can watch the latest videos on our website. We'll discuss about position, displacement, velocity, and acceleration. You know, all of them are related. Here are a few graphs which will give you an idea of type of examples which we are going to take in this particular video. I hope that will help many students who are starting with physics and who are also doing mechanics and other related subjects. Let us begin with some basic definitions. So here are a few terms which have been defined. Kinematics. As you know, kinematics is the branch of physics that deals with the description of motion of objects without reference to force or agent causing the motion. So that is kinematics. When we talk about dynamics, in that case, it is the branch of physics that deals with both the motion of the bodies and the forces that produce it, right? So that gives you clear distinction between the two terms. Now we'll define vectors and scalars. Vectors are quantities that have magnitude and direction, and scalars are quantities that have only magnitude, right? Example for vectors are position, displacement, and velocity. We are going to study their graphs in this particular video. And scalar quantities are time, mass, length, speed, and distance, and many others, of course. So let's define what is position. Position is the place where the object is located. It is a point of reference and direction, right? So it has a point of reference and direction. Now, displacement. Displacement describes the magnitude of change in position and the direction of that change. So both magnitude and direction, it is a vector quantity. Velocity is rate of change of position, acceleration is rate of change of velocity, and when we talk about distance or directed distance, right? Distance or directed distance, both are scalar quantities. Both are scalar quantities. We only measure the magnitude of the distance covered. Okay, let's take up examples to see how all these quantities are related in graph. So we'll begin with example 1, which is uniform rectilinear motion with constant velocity. So constant velocity means a car moving at a constant speed of, let us say, 60 kilometers per hour, right, in a particular direction. So that becomes a constant velocity. Position of an object is shown with reference to the fixed point, the origin, right? So that green line is a graph of position of an object with time, right? So here we have distance in meters, time in seconds, and the graph here is shown, which is this displacement time graph. Now the question is, describe displacement, which is change in position, and find velocity, right? That's the question. So what we are going to do here is we're going to study displacement in smaller units. Let us first consider the first second. When I say first second means from 0 to 1 second. So this portion, let's try to analyze this portion. Now here, what do you notice? You notice that the object starts from a distance which is 10 meters, let us say on the south, and is moving towards north, and it comes closer to the point of reference, and it's only 5 distance away from there, but still in south direction. So we'll find the displacement of this object in the first second, right? That's what we are going to do now. So in the first second, the object moves from minus 10 meters to minus 5 meters. The displacement, which is the change in position, right? So it is the change in position, that means d2 minus d1, right? So as we can see here, displacement is what? is change in position. That is d2 minus d1, correct? So delta d, that is what we are referring this as, is equal to d2 is minus 5. So minus 5 minus minus 10, that gives you 5 meters. So the object has moved 5 meters in a positive direction, which we'll consider north. So normally we'll consider positive direction towards north or towards east. So these two directions, north and east, will be considered positive for us. Now let us analyze the second. So second is from t equals to 1 to t equals to 2. In this period, the object moves from minus 5 to 0. So let's find the displacement, which is 0 minus minus 5. Again, 5 meters in this second. So in the second also, the object's displacement is 5 meters. Now let's find the displacement between time t equals to 1 to time equals to 4. So between time 1 to 4, that is this much. So the displacement is, as you can see here, that reflects the displacement on the straight line shown as the graph for displacement. Okay, so d4 minus d1 is 10 minus minus 5. That gives us 15 meters. So the object has moved 15 meters during this interval. Now what is the average velocity between time 1, t equals to 1 to t equals to 4? Well, the velocity is rate of change of displacement. So that is what it is, rate of change of displacement. We know displacement d4 minus d1 is 15 and the time interval is 4 minus 1, which is 3. When you divide, you get 5 meters per second. So units for displacement is meters and for velocity in this case is meters per second, correct? So that is how we can find the average velocity between these 2 points. Now, when the displacement time graph is a straight line, as you can see, in that case, the instantaneous velocity is same as the average velocity, right? So we have constant velocity. As you see in this case, it is 5 meters per second, and that is basically the slope of or the gradient of the curve, correct? Correct. So that is a short note mentioned here. Velocity, the rate of change of displacement, is the slope at any point on this graph. Now, since this is a straight line, we found the slope between these 2 points, correct? And that was the velocity 5 meters per second. You have also understood now that uniform linear motion is one-dimensional motion along a straight line with constant velocity. Motion in one direction is considered positive and other directions negative. Normally, movement along east or north is considered positive direction. Perfect. So I hope you have understood what is uniform rectilinear motion, correct? With constant velocity. Now let's take up another example. In this particular case, we have different legs in which the velocity is constant, but overall it changes. Example 2 here is uniform rectilinear motion in one direction. That means the object is moving, let us say, in the positive direction towards north. Position of an object is shown with reference to a fixed point, the origin. Analyze the graph for displacement, time, and distance. So again, we'll divide it into 3 portions. The first one, as you can see, this particular straight line, which is kind of increasing with a constant rate. And then we have a standstill position. Distance is not changing. And then we have a position where the distance is increasing linearly. So we'll have these 3 intervals to be analyzed. First one, time duration of 0 to 4 seconds. In this duration, the displacement is d4 minus d0, which is 8 meters. Velocity in this particular interval is 8 divided by the time duration of 4. That gives you 2 meters per second. So the velocity is constant 2 meters per second, and as you can see here, the velocity is sketched right there, 2 meters per second, correct? So that is the velocity shown to you. Now, let us look into the second interval where the object is stationary. It is not moving at all. So from 4 to 8 seconds, as you can see, the distance is not changing. So d8 minus d4 is 8 minus 8, which is 0 meters per second. Since the object is stationary, it is not changing at all. Numerator is 0. Dividing by the time duration gives you 0. So the velocity is as expected, 0 meters per second, correct? Let's consider the last leg where the distance is increasing at a constant rate. Constant rate means the velocity is constant, correct? Let's calculate. So between 8 to 12 seconds, displacement is 12 minus 8, which is 4 meters. And the time, change in time, is from 12 minus 8, which is also 4. Dividing 4 by 4, what we get? 1 meters per second. So the constant velocity of 1 meters per second is the result. As you can see, we have drawn the velocity time graph here, right? So that is the velocity, which is velocity of 2 meters per second, correct? So here v is 2 meters per second. And then we have indicated velocity of 0 right there. So that is velocity of 0 meters per second. And then we have velocity of 1 meters per second in the last zone, velocity of 1 meters per second. Is that clear to you? So the velocity is also shown here. However, the scale is different, right? But just to give you an idea, we have shown velocity using the scale meters per second on this particular graph itself. Now, let us also consider the distance traveled. It is important to note when the object moves in one direction, right? So distance is the magnitude of displacement when the direction is not changing. So if the direction is not changing, it is moving in one direction, then distance and displacement magnitudes are same, correct? So the total distance covered in this case is 12 meters from 0 to 12, right? So that is 12. So this coordinate point here is basically 12 seconds, right? And 12 meters. Okay. So the duration is 12 seconds, and therefore the average velocity in this case is 1 meter per second. Okay. Now let's talk about acceleration. Acceleration in each interval is 0 as the velocity is constant. Whether it is a constant value, which is more or less than 0, or it is 0 exactly, but it is constant, right? Velocity and acceleration is not defined at the point showing discontinuity or the corners. So when you actually consider this corner at this point, the velocity and acceleration is not defined since we cannot exactly find the rate of change at this point, right? We do know the rate of change before and after this point, correct? Okay, let's move on and take up the next example, which is example 3. Uniform rectilinear motion, change in direction. So this time we have a change in direction. As you can see now, the distance decreases at the end, right? So position of an object is shown with reference to the fixed point, the origin, describe displacement, velocity, acceleration, distance, and speed in this particular case. Again, we'll analyze this in 3 intervals. The first interval in this case being from 0 to 4, where the distance is increasing at a constant rate. And then we'll take up the portion where the distance is stationary, not changing, stationary, not changing. The velocity is 0, correct. And then when the distance or the displacement is decreasing, correct. Now, it is important to understand whether the displacement is increasing or decreasing. Distance is always increasing, you correct? Because you're moving rather maybe in positive or negative direction, maybe north or south, but your covered distance, right? So the magnitude increases. Okay, let's analyze these situations beginning with the duration from 0 to 4 seconds. So in this particular duration, the slope indicates the velocity and difference between final and initial position is the displacement. So change in this position is the displacement, which is 8 meters in this particular case. Now during this interval of 4 seconds, 8 divided by 4 gives you 2 meters per second as the velocity. Now this is the average velocity and also the instantaneous velocity. Since at any point you have the same slope, and therefore the velocity, which is average or instantaneous, is 2 meters per second in this particular case. Now let us consider the duration between 4 to 8 seconds. In this, we see that the object stays at a point. Distance is not changing. 8 minus 8 is 0. That gives you 0 divided by the time interval, velocity of 0 meters per second. Well, velocity is 0 and acceleration will also be 0. Now let's consider the last phase, duration 8 to 12. What do you notice? You notice that the displacement decreases. So delta D, which reflects the change of position, D12 minus D8, 4 minus 8 is minus 4. It is negative. So the object is coming closer. It's not going further. In this particular case, you will notice that change of displacement, change of position over change in time is minus 4 over 4 minus 1 meters per second. So the velocity is negative. Object is now approaching rather than moving away. That is what this minus sign indicates. Clear? Now let us consider the speed and the distance. Total distance covered in 12 seconds, which is the time period, is 12 meters. It was 12 meters. Why? Because the object moved up. First it went away 8 meters, correct? And then it came down by 4 meters. So the distance traveled, d, is 8 plus 4, which is 12 meters. Is that clear to you? So basically what we do is we add the absolute values of displacement to get the distance, right? So that is the key. So to find the distance, what do we do? Add absolute values of displacement. Correct? This is for distance. Perfect. So that is how you get the distance. Now, let's find what is the average speed. Average speed, mind it, it is a scalar quantity. Total distance over total time, 12 over 12 is 1 meters per second. Clear? Now let's talk about acceleration in this particular example. Acceleration in each interval is 0 as the velocity is constant. Velocity and the acceleration are not defined at the points where it shows discontinuities or the corners. So these points it is not defined. Same as before, right? Example 4. This time we'll consider distance, net distance and average velocity. Net displacement and average velocity. So again a position is given to us of an object with reference to a fixed point which is origin. We'll again consider these intervals from 0 to 12, total interval this time. So when you consider the total interval between 0 to 12, in that case time taken is 12 minus 0, which is 12 seconds, correct? As far as the displacement goes, it started from 0, but it is ending at a position which is for us 4, right? So which is 4. So this point here is 12, 4. Correct. And therefore, the displacement in this case is d12 minus d0, 4 minus 0, which is 4 meters. So we got the displacement. So when we say average velocity, the term velocity is important to understand, is displacement over time. That gives you average velocity. So in this case, displacement is 4 meters and the time is 12 seconds. So we get the average velocity of 1/3 meters per second. Okay. Now, let us consider the same interval and we'll now find the distance traveled, and the average speed. So in the same interval, time duration again is 12 seconds as we did earlier. However, what is the distance? Well, the object went up 8 meters, came down 4. So we'll add the absolute values to get 12 meters as the total distance. So average velocity is the distance over time. So 12 over 12, which is 1 meter per second. You get the idea. So in this case, the speed is much more than the velocity, mainly because there's a change in direction. So consider final and initial displacement for average velocity. That is what we did here in this first case. And as far as average speed is not the magnitude of average velocity. That is very important to understand. Average speed is not the magnitude of average velocity. Clear? It is different. And as you can see, we got different values also. Correct? If the object changes direction, then the average speed is greater than the magnitude of average velocity. Clear? Now let us consider example 5, non-uniform linear motion. Position time graph is not a straight line for a non-uniform linear motion. We need to find displacement and average velocity in the interval 0 to 5 seconds, and we need to determine instantaneous velocity at 5 seconds, right? So you are given a graph here. So when you work with the graph, we get approximate solutions. Correct? The idea here is to understand the strategy. Okay, so let's begin with a time interval which is given to us from 0 to 5 seconds. So we'll work in this time interval 0 to 5 seconds since we need to find the displacement and the average velocity between this interval of 0 to 5 seconds. Now, from the graph, we can read a value. A is 5, 2.5. So that shows that within the first 5 seconds, the displacement is 2.5. So we get the idea of displacement 2.5 minus 0, that is the value. The average velocity will be change in displacement over change in time. Time is 5 seconds, so that gives us 0.5 meters per second. So this is the average velocity during that interval from 0 to 5, correct? Now let us find the instantaneous velocity at t equals to 5. So that is the second part of this, to find instantaneous velocity at t equals to 5. So at this particular point, to find the instantaneous velocity, what are we going to do? We have to draw a tangent, right? So that is the first thing. Draw a tangent at t equals to 5. So we have shown a dotted line in orange for the tangent which is shown there. Now the coordinates of the points, let me write them big and bold. The point Q is 7.55 and the point P is 2.50. So the velocity is the slope at this particular point, slope of the tangent, right? So slope of the tangent is what we'll consider now. So slope of the tangent is the instantaneous velocity. So it'll be 5 minus 0 divided by 7.5 minus 2.5. So there is an error here, 2.5. Okay, so that means 5 over 5. And that gives you 1 meters per second, correct? So the slope of this tangent is 1 meters per second, correct? So that is how you will find the velocity at a given point. Now, we have to sketch the velocity also. So let us extend this. Sketch velocity. We know velocity to start with was 0. At this particular point, let me use a different ink. We get the velocity, which is 1 meters. So let's say the scale is changed to 1 meters per second. In that case, each division is 0.5. So 1 meter is this point. At 5, it is 1.1 meters. So we'll just connect the origin with 1 meters and draw a straight line, correct? Representing that as our velocity, right? So we'll not write the value. We'll just say the velocity graph is in green, correct? So the red graph sketch. So the velocity graph we have sketched in green as shown here. It is connecting the point 0 to the value which we just calculated, and we just sketch this particular graph. That straight line indicates the velocity. Okay, so that is what is the velocity graph for us. And at every point, you just draw a point and the tangent. That gives you the velocity, correct? To make it simple, we assume that's a linear function, right? And so we join 0 with 1, the value calculated here, to draw the graph of velocity. Okay. Now let us see what is the acceleration. Well, the acceleration is rate of change of velocity, right? So in this particular case, we got a velocity of, let's redo this, okay, there's a calculation error. So change in velocity in the first 5 seconds was 1 meters per second, right? 1 meters per second divided by 5 seconds, so we get constant acceleration of 1 over 5 meters per second squared, correct? So that is how we get our acceleration in this particular case, right? So we found that we can find acceleration which is constant in this case if the velocity is a linear function, and from the slope of the line we get the constant value of the acceleration in this particular example. Perfect. So that is how it is to be done. Let's move on and take the next example, which is non-uniform motion. So in this case, the first part of the graph is non-uniform. It is increasing, first slower and then faster. Do you see that? So all over, there is an acceleration. That is what it is. A parabolic path in the first 4 seconds indicate that the object starts with initial velocity of 0 from the origin, and then displacement increases rapidly. Velocity, the rate of change of displacement, will be constant. Slope of tangent on points of the parabola will be the velocity. Velocity is assumed to be linear here, correct? So we'll assume linear velocity in this particular case. So let's work out the velocity also. So let's consider the duration from 0 to 4 seconds. In this, the displacement is 8 meters and the velocity is assumed to be linear in this duration. At the origin, the velocity is 0. So at this point, velocity is 0. Let's find the velocity at another point. So in this case, we are considering a point which is at V2. So that is at t equals to 2. We're considering a point. We're drawn a straight line as a tangent. So we have drawn a tangent here. And slope of this tangent is 4 minus 0 over 3 minus 1. We have 2 meters per second. That is the slope of this tangent. And that gives you the velocity v at the particular point t equals to 0. Clear? So we have 2 meters per second. Now, to draw the velocity function, what we could do is we could take 2 as a point, 0 and 2, and then extend it. That is what we've done. So to just enlarge this particular view, let us say we want to draw now velocity which is in meters per second, correct? And this is time in seconds. So we know the velocity is 0 at this point, but we know at 2 it is 2, right? So at 2 it is 2. So joining these 2 points, we get a velocity graph. You get the idea. So that gives you the velocity graph. The equation which we could write is v of t is basically equals to t. That line equation can be given like this, correct? That is what we've written here as a general equation for the velocity for the given situation, correct? Now let us consider the other part, which is from 4 to 8 seconds is stationary. The object is not moving. Displacement is 0. velocity is also 0, correct? Now the third half is when the displacement is decreasing. It comes to 0. Do you see that? It comes back to the starting point. Okay, so the displacement d4 to um, okay, so during 8 to 12, what we notice here is that at 12 the displacement is 0 and at 8 it was uh, 4. Let me make the correction here. Displacement is 0, right? So d12 is 0. 0 minus 8 is minus 8. Right? That is what it is. And the velocity is constant here, which is rate of change, which is minus 8 by 4, or basically, which is equals to minus 2 meters per second. So in this case, the velocity is minus 2 meters per second, but it is constant. And this minus 2 meters per second is shown here with the with this particular line, correct? So this line indicates the velocity of minus 2. This line indicates velocity of 0 because it was stationary, and the line before that, the increasing velocity, is shown in a straight line. So that is how we could draw the velocity graph also. Now you can notice that the acceleration, the rate of change of velocity is 1 meters per second in the interval 0 to 4, which is from the equation of the velocity graph, right? And after that, the acceleration is 0. So only acceleration is in the first 4 seconds, which is 1 meters per second square. I hope this concept is absolutely clear. We have taken one part of the curve where the rate of change is nonlinear. Okay, now we'll take the next example, example 7, non-uniform motion. So here, the object is stationary in between, but in the starting, you see this curve, and at the end also, it is curving. The two curves are kind of different. In the first case, the position increases slowly and then fast, and in that next case, it slowly decreases and then increases. Do you see that? It's like increasing in negative direction as it comes down. Now the question here is, use the graph to answer the following questions. Find the average velocity on the interval 0 to 4. Find the instantaneous velocity at t equals to 0, at t equals to 8 and t equals to 10, a point here and a point on the later half. Draw a velocity time graph in the interval 8 to 12. Find acceleration in the interval 8 to 12. So let's begin with the first part. We have done at length this earlier also. So during 0 to 4, the displacement is from 0 to 8, right? That is 8. So the displacement is of 8 meters. Average velocity being 8 meters divided by the time taken of 4 seconds. So that gives you 2 meters per second as the average velocity. Now, to find the instantaneous velocity at t equals to 8, which is a point around the horizontal, so it is equal to 0 since it is horizontal, correct? Now let's find what is the velocity at t equals to 10. So draw a tangent at t equals to 10, right? And then find slope. That is how we do the velocity. The slope of this tangent which is drawn here is minus 2 meters per second. So that becomes the velocity at 10, correct? So you do rise over run on this particular graph, and then you get your answer. Now, let's look into the velocity at the instance. We know velocity at 8 is 0, velocity at 10 is minus 2. That means that the velocity is decreasing. And so what we've done here is we've taken at 0 and then at 2 and connected these points with a straight line to give you velocity time graph. We know it is a straight line. So we got those points and then we connected them to get the velocity time graph, correct? So since the velocity is linear, join the points and extend as shown in the figure. As far as acceleration is concerned, acceleration is rate of change of velocity. In the first half, it is increasing, right? So first it is 0 and then it is pretty high. And so we have the rate of change of velocity is minus 1 meters per second square in the interval 8 to 12. In the later half, it is 8 minus 1, but in the first half, it is increasing. We didn't really calculate since we were supposed to find acceleration in the interval 8 to 12. Okay, so in the interval 8 to 12, we can find the slope of this, which is minus 1 meters per second square, right? So that becomes the acceleration in this interval, rate of change of velocity in this interval. So that is how you find the acceleration. So I hope with that you understand how do we analyze position time graph. So we had a straight line change in position with a constant rate, which is velocity, and therefore we have velocity equals to 5 as a horizontal velocity all along. In the second case, we had three different legs. Here the object is not changing, so the velocity here is 0, right? This is velocity of 0. Here the velocity is positive 2, and here it is positive 1, correct? Increasing at a constant rate. Then we calculated velocity as positive 2, 0. Since it is dropping down, it is minus 1. The units for velocity we are taking as meters per second, right? For a non-uniform motion, we'll have to plot the tangents at the point to find the instantaneous velocity. Now we know in this case at origin the velocity was 0. So what we did was that we found the instantaneous velocity, connected the two with a straight line to draw the graph for velocity, since we assume that that will be increasing at a constant rate. Acceleration will be 0 in this case. In this case the acceleration will be slope of the velocity graph, right? So acceleration slope of tangent on velocity time graph, correct? So acceleration was 0, a is 0 in this all the three cases, correct? But here we have acceleration, which is the slope, and we can find the slope as the point between 1 over 5, right? So acceleration was 1 over 5 meters per second in this particular case. Now, wherever we have a non-uniform increase or decrease in displacement, we'll have a velocity which will be a value increasing at a constant rate, and then we'll have a constant value of acceleration also, as you have seen in these three examples, correct? So I hope with this you understand how do we analyze position, displacement, velocity and acceleration from the given position displacement graph. Feel free to write your comment, share your views, and if you like and subscribe to my videos, that will be great. Thanks for your time and all the best.